You ever wonder if there's a hidden language that connects, well, everything? A kind of mathematical Rosetta Stone that could describe the patterns you see in nature, in computer code, and even in how we think? Well, that's exactly what we're diving into today. Let's see if we can crack the code together. So just think about that for a second. I mean, on the surface, those things couldn't be more different, right? One's about AI learning, another is about how complex systems regulate themselves, and the last is about, well, the nuts and bolts of software. But what if I told you they all operate on the exact same deep, fundamental principles? Because that's the secret right there. These incredibly complex, totally separate systems, they're really just different flavors of the same underlying patterns. And the key to actually seeing this hidden architecture is a branch of math called category theory. Okay, so here's our game plan. We're going to start with why anyone even needed this new kind of math in the first place. Then we'll get into its basic grammar, the building blocks. After that, we'll look at some mind-blowing applications in computing, see how it's shaking up math itself, and finally, we'll wrap up with the real power behind this whole way of thinking.
All right, first up, a search for patterns. To really get why category theory was such a big deal, we got to go back and look at the problems that had mathematicians kind of stumped in the early 20th century.
So this quote from Saunders, one of the creators of all this, it really hits the nail on the head. For the longest time, math was built on something called set theory. Now think of set theory as just a list of all your Lego bricks. You know, you've got 10 red 2x4s, 15 blue 1x2s. It's great at telling you what pieces you have, but it tells you absolutely nothing about how those pieces connect to build a spaceship or a castle. It describes the parts, but it completely misses the blueprint for how they all work together. And that blueprint was what they were missing. So how'd they fix it? Well, that brings us right to our second section, the language of structure. They realized they didn't just need new equations. They needed a whole new grammar, a new way to talk about relationships themselves. So picture this. It's 1945. Samuel Eilenberg and Saunders come along and introduce this radical new idea. Their goal wasn't to throw out all the old math. Not at all. It was to build a new layer on top of it, a kind of meta language that could compare completely different mathematical worlds and find the deep connections, the natural equivalences between them. So the first building block is the category, and it's actually super simple. A category just has two things, dots and arrows connecting the dots. That's it. The dots are your objects. They can be literally anything, numbers, people on social media, websites on the internet. The arrows are the relationships or the actions between them. So in a category of your family, the people are the objects, and the arrows could be things like, is the parent of, or is the sibling of. And here's the key idea. The arrows are just as important as the dots. We're not just listing family members anymore. We're actually mapping out the entire family tree and how it functions. Okay, next up, functors. Now, if a category is like a map of the New York subway system, a functor is like a guide that shows you how to translate that map to the London Underground. But it's a really smart guide. It doesn't just randomly plop you down in a new city. It maps stations to stations. And, this is the crucial part, it makes sure that if two stations are connected by a line in New York, their matching stations are also connected in London. It translates the system while perfectly preserving its structure. It's how we can suddenly see that, hey, a family tree and a company's org chart might actually be the same kind of map. And this is where it gets really meta, but stick with me. Finally, we have natural transformations. So imagine you have two different ways of translating a book. Say you use Google Translate, and you also hire a professional human translator. Those two translation methods are your two functors. A natural transformation is what lets you compare those two translations, side by side, page by page, to see exactly how they relate to each other. So we're not talking about the book anymore, or even the translated versions. We're talking about the process of translation itself. It's how we compare the blueprints. So you see how it all fits together, right? You've got categories, which are like your different domains of knowledge. You have functors, which are the bridges connecting those domains. And then you have natural transformations, which let you analyze the relationships between those bridges. It's a complete grammar for talking about pure structure. Now for the really, really cool part. Section 3, a code for computation. How does all this abstract grammar stuff actually apply to the real world, specifically to computer science? Well, get this. Take AI and supervised learning. It turns out that backpropagation, the core algorithm that lets a neural network learn from its mistakes, is a perfect real-world example of a functor. This means that learning isn't just some weird magical black box. No, it's a structure-preserving translation. It's a formal way of saying the network is methodically mapping its errors back through its own architecture to get better. This gives us a way deeper understanding of how AI actually works.
Then there's this, and you gotta love the name, cybernetic kittens. This project uses category theory to find a common language for all sorts of self-regulating systems. We're talking everything from the stock market to the thermostat in your house. By finding the shared patterns, they can build these universal models to understand how these crazy complex systems manage to stay stable and, not fly into chaos.
And finally, profunctor optics. Okay, I know, it sounds super intense, but the idea behind it is actually pretty brilliant. It's a powerful way to track how data flows through a piece of software. It lets you build programs like you would with Legos, using these simple, predictable, reusable pieces that you can just snap together to build something incredibly complex without it falling apart. It's the whole idea of compositionality made real.
So, just to recap these amazing applications, we're modeling how AI learns. We're making sure that complex dynamic systems don't just collapse. And we're analyzing the very flow of information in our code. This is not just some abstract theory anymore. It's a serious toolkit for building and understanding the systems that run our modern world.
But the impact, it goes even deeper than that. Which brings us to Section 4, New Foundations for Math. Because category theory is so fundamental, it actually gives us a whole new lens for looking at mathematics itself. And this is the core philosophical shift right here. Traditional math, the kind based on set theory, is like a dictionary. It's obsessed with defining what things are based on their internal properties. But category theory, it's like a grammar book. It could care less what things are. It's totally obsessed with what things do and the rules for how they can be combined. It's a massive shift from a static universe of objects to a dynamic universe of processes and relationships.
And this new foundation is what's paving the way for some of the most mind-bending ideas in math today. It's the language that powers concepts like homotopy-type theory, which literally treats mathematical proofs as shapes, and the univalence axiom, this radical idea that says if two structures are logically equivalent, then for all practical purposes, they are the same thing. This is the stuff that's trying to build a unified foundation for all of math and computation.
And all of this brings us to our final section, and really the main point of this whole explainer. Section 5, the power of abstraction.
And here it is, the most important takeaway. We tend to think of the word abstract as meaning vague or disconnected from reality. But what category theory shows us is that true abstraction is the exact opposite. It's not about ignoring details. It's about figuring out which details truly matter. The underlying structures, the relationships, the patterns that are the same everywhere you look. It's a tool for seeing the world with incredible, surprising clarity. So that's the thought I want to leave you with. If you start focusing on relationships instead of just objects, on what things do instead of just what they are, what kind of universal patterns might you start to see in your own work, in your field, or even just in your day-to-day life? The Rosetta Stone is right there in your hands. What will you decipher?